Welcome, ladies and gentlemen, to this video lecture. So, we have previously seen some examples on quantifiers and quantified statements. Now, let us talk about how to prove quantified statements, of which you will have noticed that the definition of a limit is an example. And a complaint that students have when they start off in the field called analysis. This is the subfield of mathematics in which the definition of a limit fits in. One thing that beginning students often struggle with is that they do not know where to start. That is not because you are stupid. That is just because you are inexperienced. I myself, it took me a long time to come to grips with how to write a proof of a quantified statement and where to start and what to do. So before you start writing a proof of a quantified statement, I would suggest that it is very important to write a plan before you start. And writing out the plan, or laying the foundation, building the scaffolding, that is purely mechanical. There is no thinking involved. But it frees you from let's say, thinking about how to structure your argument, and you can focus on the most difficult parts. You can focus on the parts that actually require some thought. Okay, so let us do some examples of how to structure a proof, and we will do it in the abstract, just to emphasize that it is always the same. It is always the same. And you can do it without thinking. So let's start with A, B, and C sets. So they can be anything. And we've got some predicates. Let's say we've got U, the predicate U, which takes as input elements from the Cartesian product of A and B, and it maps to true or false. And we've got a predicate V, and it takes inputs from our set C, and it maps to true and false. Let's write a quantified statement involving these sets A, B, C, and the predicates U and V. So for every A in A, there exists a B in B, so that for every C in C, we have that if U A B is true, comma, then V of C is true. So here we have a quantified statement. It is entirely abstract because we didn't say what these sets A, B, C, or these predicates are. But you can recognize it as quite similar to the definition of a limit. And in the very near future, we will start proving statements like this. And specifically proving or proving things about limits. Okay. So we will very often want to write a proof of a statement of the form that we have just written down. Now, what you should do always is, before you do anything, it is a very good idea to write down a proof outline. And you might even write it on a separate piece of paper and treat it like a map. So you first write your outline on a separate piece of paper, and then once you've done that, that is a map that you have drawn and that you can use in writing your proof for realsies. Okay, so let us talk about how to write a proof outline. So let's give the statement a name. Let's call it S. So let's write a proof outline of S. So if we were going to prove S, how would a proof of the statement S look like? Of course, we cannot prove S because it is completely abstract. We don't know what these sets A, B, and C and what the predicates U and V are. But if we did know what they were, what would a proof look like? So let's take a look here. What do we have to prove? We have to prove for every A in A. So you always start from the beginning and you read it from the beginning to the end. And that tells you exactly what you need to do. So you need to, firstly, we need to do something for every A in A. So when you write the proof of the statement, what you will do is, what we want to prove is for every A in A. So the first step that you do is, what you do is you say fix any A in A. That is your first step. So that takes care of this part of the statement that you want to prove, this first quantifier. Then the next part is you want to show that there exists a B. We must show that it exists, so we must build it, we must construct it. So the next part is we should define a B and leave a blank space and put in here, I would say here in brackets, we must be sure that this B is actually an element of our set B. So that takes care of the second part. Okay, then we continue, next part, so that for every C, so again, universal quantifier, we say we fix any C in C. So that takes care of this part. So before we move on, notice here, every time we have a universal quantifier, we say fix any element from the set that we are choosing our elements from. So for every A in A, we want to prove for every A in A. So what we do in writing our proof, we say fix any A in A. Then we need to show that there exists a B. So we must show that there exists a B. So we must construct, or we must define a B. We don't at this moment know how to define this B. So that is why I leave a space here. Then we move on. So that for every C in we want to show for every C in C. So again, we say fix any C in C. Okay, and then we want to show that if U of A, B is true. So here we want to show an implication. So here we have an implication. So how do you prove an implication? You assume the hypothesis, the if part, and you then show that if you assume the if part, then you get the conclusion, the then part. So what we will do is we will write assume U of A, B is true. And now we need to do a bit of work, and we need to conclude somehow that V of C is true. And here we have our proof outline. You see, we didn't prove it, but it gives us a plan of how to proceed. So we want to show for every A in A, so we fix an A in A, that there exists a B in B. We must find it, we must define it, and we leave a blank space here. And while we are here, how do we define this B when we must show that it exists? What are we allowed to use? We are only allowed to use the symbols that we have defined previously. So here, in defining this B, we are only allowed to use our previously defined symbols. So in this case, this is this A. So I'm going to write down, maybe let's write down here, using previously defined symbols. Previously defined symbols. And the only symbol that we have previously defined is this A. So we're only allowed to use this A. Okay. And then we move on. For every C, fix any C. We want to prove this implication. So we assume the hypothesis, we assume the if part, so assume that U of AB is true. And now here we need to do a bit of work, and finally we should conclude that the conclusion of our implication is true. And here we have a proof outline. So this gives you a plan of how to proceed in writing a proof of a quantified statement. Let's do another example. Let us write down a proof outline for the negation of S. So let us negate S and write down a proof outline. So let's write down the negation of our statement. So the negation of S. So remember, how do we negate a quantified statement? You flip the quantifiers and you negate the predicates. So we start off for every A in A. That goes to there exists. Exists an A in A. So now we've done that one. Next one. There exists a B in B. So we flip the quantifier for every B in B. That takes care of this one. So that for every C in C, so flip the quantifier, there exists a C in C. Okay, and now we have to negate the predicate. So this implication, remember, the negation of an implication is not another implication. It is an and statement. So we need to negate this implication. It is an AND statement. So it is U of AB is true and V of C is false. Okay, so here we have written the negation of our statement S. Okay, let us write a proof outline of how to prove the negation of S. So a proof outline of not S. So a proof outline of this statement that we have written down. So first part is there exists an A in A. So the first thing is we must define what this A is. We don't know how to do it. So we leave a blank space. But it must be an A. What symbols are we allowed to use in defining this A? We're not allowed to use anything. So we will have to choose some constant that we know actually lives in A. We're not allowed to use any other symbols that because we haven't defined any other symbols. So we want to show that there exists an A. That takes part of that one. Then next part, for every B in B. So we will go and we will say fix any B in B. That takes care of this part. Then we need to show that there exists a C. Again, we must define it. So we define C. And we leave a blank. And this C should be in C. And what are we allowed to use in defining the C? We are allowed to use our previously defined symbols. So we are allowed to use A and B in defining our C. We are allowed to use A and B. We are only allowed to use our previously defined symbols. Okay, so that takes care of defining C. And then what do we need to do? We need to show that U of AB is true, so we need to show U of AB is true. So this will be one part. Here we need to do a bit of work. And we want to show an AND statement. We also need to show that V of C is false. So we need to show that not V of C. And here we also need to do a little bit of work. And here is an outline for proving the negation of the statement S. Here we have written down the negation of our statement S, and here is an outline of how to go about proving such a statement. So we have done this in the abstract. We don't know what these sets A, B, and C and what the predicates are. But if we did know, and if we wanted to go about proving this statement S, this is what our proof would look like. And the benefit of writing an outline first is that it helps you to understand what you should do, where you should start. So it saves you from that problem that you may face, that you do not know where to start. Where do you start? You start by writing down an outline, and that gives you a plan or a map that you can follow down the path of completing your proof. And it will be very hard in the beginning that is, let me warn you, it will be very hard in the beginning. But that is not because you are stupid. That is because this stuff is very, very hard. And this is your first steps in what we will call, or what some people call, real mathematics. No longer just calculating of integrals, no longer getting numbers as your answers, but constructing proofs of general statements. That is the mountain that we are climbing. We become less and less focused on calculation, and more focused on proving general statements. And you will also see, as we go along, if I remember to emphasize it, that if you can prove general statements, it saves you from having to do the calculations. There is this old adage that mathematicians are the laziest people in the world. They don't like doing calculations. You make mistakes doing calculations. So you want to do as few calculations as possible. If you can prove in general that a certain situation holds true always, then without you needing to do the calculation, that is always better than needing to slog through an unnecessary calculation in which you may inevitably make a mistake anyway. So that is the road that we're walking down, and the goal that we have in this chapter. Okay, but it will be a long and a hard slog. I will see you on that long, hard slog in the next video.